Foundation models now demand training clusters exceeding 100,000 GPUs. Yet at this massive scale, millions of dollars in compute time are routinely wasted. When these massive systems stall, the industry's default response is to purchase increasingly expensive, vertically integrated proprietary hardware fabrics. But the math shows that raw processor power is no longer the limiting factor. The true point of failure is the synchronization pipeline itself. Specifically, the massive telemetry overhead required to coordinate simultaneous global gradient updates across the entire cluster. This manifests as the straggler effect. In large language model training, hundreds of parallel data streams converge for gradient updates. If one single stream lags slightly behind, it forces the entire system to halt. A single delayed node suffering from tail-end latency acts as a universal roadblock. Tens of thousands of other GPUs sit completely idle, burning capital while waiting for that lone parameter update. Classical software-defined networking controllers exacerbate this delay. They evaluate scalar metrics, like queue depth or jitter, independently and reactively, treating the network as a series of physical, continuous space events. Exascale network congestion is a problem of classical mathematics and reactive routing. Faster physical cables cannot solve a structural data flow issue. The alternative shifts the focus from physical hardware constraints to a purely mathematical overlay. This white paper from Tensor Networks outlines this architectural leap, identifying telemetry overload as the primary threat. Under the core problem, classical SDN fails as networks scale because controllers are overwhelmed by hyperdimensional data, suffering from the curse of dimensionality. The proposed solution is the Predictive Tensor Control Plane, or PTCP. PTCP functions as an algorithmic overlay. Tensor Networks positions this as the arm of AI infrastructure, a software framework licensed as IP, not a hardware upgrade. This ecosystem is powered by a foundational concept known as Tensor Network Quantum Gravity, or TNQG. Instead of mapping a continuous spatial grid, TNQG calculates physical distance purely from interaction capacity, or entanglement. Inactive sectors are mathematically coarse-grained, saving massive compute cycles. This approach allows standard top-of-rack switches to function as predictive, tensor-native AI networking nodes. How exactly does an algorithm predict network congestion before a single packet is dropped? The answer relies on a mechanism called bounded memory states. PTCP utilizes a pattern-of-life tensor train, or POLTT, algorithm. It takes the sprawling, chaotic, hyperdimensional telemetry of the network and compresses it into a highly structured, bounded probability tensor. This compression mathematically limits the memory footprint. It forces the data volume strictly to O of dr squared. This hyper-efficient telemetry extraction occurs entirely at wire speed, utilizing an eBPF-powered architecture directly in the kernel. With this bounded tensor, PTCP calculates the conditional value at risk, or CVAR, representing the probability of developing network congestion in the immediate future. Based on that CVAR calculation, the system dynamically routes traffic along predictive geodesic paths, the most mathematically optimal routes available. By anticipating congestion horizons before they form, PTCP maintains lossless, tail-latency-free parameter synchronization across the entire AI fleet. This shift to tensor-native mathematics directly and completely modifies the fundamental cost-benefit analysis of the entire data center. The white paper's cost and risk mitigation matrix details these impacts. The second row highlights energy consumption. Classical compute nodes draw massive power indiscriminately, threatening climate goals. To address this, PTCP incorporates an energy and operating cost variable, denoted here as CE. By structurally embedding this variable directly into its routing math, the system natively steers computational workloads toward geographic regions that currently have a surplus of renewable energy. Moving forward, the matrix also directly addresses critical cybersecurity risks. Legacy defenses rely on deep packet inspection, which creates latency drag on AI workloads and fails to catch zero-day lateral movements. PTCP models network traffic as a geometric topology. When lateral movement occurs, it registers as a structural defect, and the system immediately isolates it without scanning the underlying data. This distortion is quantified by the D-topo score, flagging defects by measuring the anomaly's gradient magnitude. Because the inspection is payload blind, the kernel executes automated quarantines instantly without impacting network speed. Finally, there is the existential risk of vendor lock-in, caused by dependence on vertically integrated fabrics like InfiniBand. PTCP is packaged as a hardware-agnostic Docker container, aligned with standard hardware like Intel Atom and Xeon D. This software allows cheap, open network white box hardware to match or exceed the performance of proprietary AI fabrics. Migrating core infrastructure for multi-billion-dollar AI clusters carries extreme risk. Fleet architects must verify the mathematical outcomes before shifting live production traffic. The white paper provides a specific deployment strategy designed to deliver this proof, the Shadow Mode Pilot Program. The first step is zero-risk testing. The PTCP container is deployed solely to ingest existing network telemetry via eBPF, without actuating any live routes. Next, the engine runs its POL-TT compressions and CVAR calculations in real time alongside the live network, generating predictive routing paths in shadow mode. The pilot is successful once the algorithm mathematically proves it mapped and predicted the exact congestion the classical network failed to avoid. Hyperscalers no longer have to choose between the steep vendor lock-in of proprietary fabrics and the reactive limitations of standard Ethernet. Escaping the exascale bottleneck is not achieved by laying more cable or buying faster physical switches. It is achieved by mastering the tensor-native mathematics of the network itself.